Okay, this was a great question, question 8 from our assignment, well, from our in-class assignment, if you like, and this is the one that we were told to hand in, or asked to hand in. Let me just straighten out the camera here. Whoops, hit it with my calculator. There we go. And this question, see on the camera, left is right, right is left, and up is down, and I can't seem to remember that. So light of a wavelength, 1090 nanometers, was detected as being emitted from excited hydrogen gas. Okay, from what energy level would an excited H atom electron relax if it fell to the third during this transition to the third level? So let's sketch out what we know. Okay, we are given that from what? So we don't know what this higher level is. N is equal to question mark. We do know, by the way, that this is hydrogen, and therefore I'm going to write this in right away, that Z is equal to 1 in any formula that I'm going to use. So I don't know that, so I don't know how many dashes to put in between, but I'm just going to do this and put N equals 3 down here. So I'm not implying that that's the fourth. I really don't know what it is, but I just don't know how many lines to put in between. Okay, so I do know that the electron started here and has dropped down to the third. So there's my electron relaxing. And the energy difference is conserved here because that energy is going to squeeze out, right? And the delta E is equal to the energy of this, not this one, but this one, because it's always final minus initial. So let's just write it as final minus the energy of the initial, and not put in those specific numbers at the moment, because again, I just want to teach you a general approach to these types of questions that'll work each time. And that energy is emitted as light. So that change in energy is actually equal to, and this is how our two sets of formulas go together, that is equal to my hc over lambda, or simply h mu. Because what is being released here as radiation in my wavy line, what's being released is electromagnetic radiation. It is light, and therefore photons. And each photon has an energy of h mu, or hc over lambda. Okay? So that's how everything goes together. So in order to figure out where it started, where did it come from, I actually am going to start with lambda and then figure out what the energy, because this equals E, what energy of radiation has that wavelength, and that photon is the one that's being, one of the many that are being emitted, but that energy is equal to the energy difference. So then that energy I will equate to delta E. That comes from the difference between the final energy value and the initial energy value. And my only unknown will be N, because as you know, that formula is composed of Z, which I know to be 1, and the constant RH. Okay, so let's do this. So the first thing I'm going to do is figure out what this energy is. So the hc over lambda is equal to energy. I know that, but in fact that's what that energy is equal to, the energy difference between these two values. And so let's calculate it. I have 6.626 times 10 Planck's constant minus 34 joule seconds times speed of light 2.998 times 10 to the 8 meters per second, and all of that is over my 1090 nanometers, which I need it to be in meters, and 1 meter is 1 times 10 to the 9, or simply 10 to the 9 nanometers. Okay, so nanometers are out, seconds and meters, and I'm going to be left with my answer in joules. And I haven't calculated this, so we're going to do this at the same time. 6.626 exponent 34 minus times 2.998 exponent 8 equals, and divide that by 1090 and multiply that by 1 exponent 9. Okay, so the energy of each photon emitted during this transition is 1.82, and there's another 2 on there, but I'll just trim it at that, times 10 to the minus 19 joules. That's the energy of each photon emitted. So every time an electron relaxes, a single photon is emitted. So because we can see this light, you can imagine how many electrons are relaxing, right? Or how many atoms there are in which electrons are relaxing. Okay, so that's that. What I'm going to do now is tell you that that energy, and let's write it. This is the energy of each photon emitted in this relaxation process. And so this is, therefore, I call it the energy emitted from the excited H atom from that electron relaxing. And so that tells me that the delta E, right, that must, if it's being emitted, it means that it's the difference between these two. So delta E is 1.82 times 10 to the minus 19 joules. Now just hold on. The change is this. Do you see why that's a negative? Can you consider why that's a negative? Think of what we said on the last question, that the change in energy is negative because it's being released, it's leaving the atom as light. And I know that a lower energy minus a higher energy, that difference is going to have a negative value. Okay, so that's why I'm putting that negative sign on there. All right, and I know that that is equal to the energy of N final minus the energy of N initial. Okay, so I have a minus 1.82 times 10 to the minus 19 joules is equal to this over here. And I know that that, one by one, I'm going to write, is a minus Z squared RH over, now not just any N squared, but N final squared, minus the energy of this, which is a negative Z squared RH over N squared, but in this case it's N initial. So change is always final minus initial. Okay? We keep that convention throughout in chemistry and most likely in physics. Okay, so then my left side is going to stay the same, so I'm just not going to repeat that on the next line. But what I am going to do is factor out my minus Z squared RH and then say that is 1 over N final squared minus 1 over N initial squared. Okay, and look, actually, why don't we write this I just said I wouldn't write it down. Well, let's carry it forward so that it's in view. Okay, I have a negative here and I have a negative here. I'd really like to wipe those out. So if I can, because this is multiplication. So basically, if I multiply both sides by -1 at this point, I can get rid of this and this. So now I'm going to go forward with 1.82 times 10 to the -19 joules is equal to. Now if you're looking at this and thinking, I know I got the right answer, but I didn't quite do it this way that she's showing me, it doesn't mean that you did it incorrectly, okay? When we've got negative signs like this, people choose to deal with them sometimes sooner than later or later, and you may have chosen to keep all of that. So it would be worthwhile to check your solution when you get it back with what we've presented here. And again, any questions, please ask me. I'm happy to help. Z, this is hydrogen, so I've got just simply 1 squared, and then it's 2.179 times 10 to the -18 joules, and then open bracket. So it would have been smart to put that down here on the denominator, and you probably did, and I didn't think as fast as you did. 1 over n final, where was I ending up? At 3, so that's 3 squared, minus 1 over n initial squared, and that is my unknown, n initial. Okay, what I'm going to do is take this and divide it by, well, 1 squared is 1. I'm going to divide it by this, and that'll isolate that side over there. So let me take, actually it's still in the calculator, my 1.82 times 10 to the -19. I'm going to divide by 2.179 exponent 18 minus, and that is, so I have a value of 0.083637, too many numbers, so I'm just going to carry them all. And when that comes over here, you see it's joules divided by joules, so those units are deleted, basically canceled, and that is equal to 1 over, my 3 squared is 9, 1 over 9, minus 1 over n initial squared. Okay? Everyone still with us? So remember, that's my unknown. Now don't do anything silly here. It's just a simple fraction, and you don't need to think about how am I going to solve that fraction. This is 1/9, so you can turn it into a decimal place if you want. Just do 1 divided by 9. Okay? And so that's going to come over there, and of course we'll have a negative sign when it moves over. So I'm going to write this as 0.083637. I'm going to bring this over, so it'll be a minus 1 over 9, and that's going to be equal to a minus 1 over n initial squared. Negative because that negative stays behind. Don't worry about the negatives, just keep going. Okay, so I still have this number in my calculator. I'm going to subtract from it 1/9, which is 0.1111 repeating. And so I get a negative, oh, look at me. Hold on. There we go. Sorry about that. I get a negative 0.02747, good, equals a negative 1 over n initial squared. And again, negative, negative. Who needs them? There you go. And so now I have 0.02747 equal to 1 over n initial squared. When it's simplified this much, I need to do 2 operations now to find n initial. First, I'm going to flip both of these, or take the reciprocal of both sides. Right? So the reciprocal, 1 over this is actually equal to n squared. And 1 over that, well, let's do it. 1 divided by, or you might have a reciprocal button on your calculator, but it's 1 divided by 0.02747. So that is 36. Okay, so this is 36.40. There's no point in carrying those decimal places. You can if you want. You'll see why in a moment. And the reciprocal of this side is n initial squared. So now I need to take the square root of both sides. So the square root of this is just simply n initial. Great, that's what I'm trying to find. And the square root of 36 is 6. So you see why I didn't bother putting the decimal places? Because n is a whole number. So yeah. Okay. So I know that some people were asking me the question when we did this. We did part of it together in class and was asking you to finish it. They said, well, I'm getting a negative equal to a square. How do I take the square root of a negative number, and so on? So I think it's really worthwhile to go back and see what we did with these signs. You've got to be thoughtful about this, and it's not only using formulas but also reasoning, like right here. Why did we put that negative sign? Oh, because it now became a change. Like, it was one thing to find E, but now that E is the change, and the change is an emission, and energy leaves the system. It's negative because I have a formula now down below that has addition of negatives. And so sign is really important. Okay? So take your time, go over this solution. If you did it, put it away actually, and take it out maybe in a week or so, and try and do that again, just to make sure that you remember how to handle these negative signs. So again, I'll reiterate, I'm going to mark these myself shortly and give them back to you, but this question 8 is a really, really good example to practice with for the exam. And let me just pull this back. You can see there's only certain things we can prepare for here to be expected to be asked, and that is, for example, with the appropriate information given, where must of the electron started from as it relaxes, or maybe you know that, and the question is, where did it relax to if given this wavelength or frequency or energy of emission. So yeah, you can see how these two formulas work together to tell the story. That's the energy emitted, but it comes from this energy difference. So there are possible unknowns in each of these areas. But remember, you should only have one unknown to find in the end. So, great question.